Hello guys, welcome back to TechDose, and in this video we will look at apply operations to maximize score problem, which is from Leetcode number 2818. Now there are a lot of prerequisites to this problem. The first one is binary exponentiation. Then you have to watch factors of a number, which will help you find the prime factorization of a given number. Then you have to know about the next greater element and the previous greater element, and you can solve the stock span or the online stock span problem. And also you have to learn about counting the number of subarrays using the count unique characters of all substrings of a given string problem. All these videos I have already made, and all the links will be present in the description below. So if you find yourself struggling with any of these topics, first you complete all of these topics, be confident, and then only you get ahead and solve this problem. Okay, now let's read the problem statement. In this problem, you are given an array nums of n positive integers and an integer k. Initially, you start with a score of 1. You have to maximize your score by applying the operation at most k times. Choose any non-empty subarray from L to R that you haven't chosen previously. That means no two subarrays can be repeatedly chosen. Okay. Choose an element x in the range of L to R with the highest prime score. If multiple such elements exist, choose the one with the smallest index. Multiply your score by x. Here nums L to R denotes the subarray of nums starting at index L and ending at index R, both ends being inclusive. The prime score of an integer x is equals to the number of distinct prime factors of x. For example, the prime score of 300 is equals to 3, because if you prime factorize this 300, it will contain 2, 3 and 5 as the 3 unique prime factors. Okay, so you have to count the unique prime factors of any given number to determine the prime score of a number. Return the maximum possible score after applying at most k operations. So since the answer may be very large, we have to return modulo 10 to the power 9 plus 7. Now if you look at the example, if you look at this first example here, it is having 83938. Now if you find out all the prime factorizations for each of this number, 8 will be represented as 2 to the power of 3, which is 2 multiplied 3 times. That means there is only one unique prime factor for it, so it will get only one score. Similarly, 3 will get only one score, 9 will get only one score, because 3 square is 9. Again this 3 will get one score, and 8 will get exactly one score. So all of them have got one prime score, right? Even though the numbers are different. Now my goal is to select k number of items from the nums, but the selection has to happen based on the scores. Okay, now we have to select the subarray which will maximize my score. So the result or the answer will always start with 1 as mentioned in the problem. Now I have to maximize my result, and in this case, if I happen to pick this 9 first, that is the subarray starting from index 2 ending at index 2, then I will be including a 9 and the k value will decrement by 1. And if in the next time I include the subarray from 2 ending at 3, where 2 scores are same, and as the problem mentions that if scores are same, we will be picking the leftmost index, so again index 2 will get picked, and so 9 will again be included. So the total score here will become 81, the resultant score, and that is how 81 has come, right? Now if you want to solve it with a simple approach, then you have to create all possible subarrays on the given array. The array length is already maximum 10 to the power of 5. So if you create all possible subarrays order of n square, that will reach to 10 to the power 10 as the subarrays count. And so this is greater than 10 to the power of 8 definitely, and that is why it will give you a TLE. So we cannot generate all possible subarrays, that's for sure. Each of the item in the array is in the range of 1 to 10 to the power of 5. And if you look at the k value, it will be in the range of the maximum count of the subarray, which is n into n plus 1 by 2 or 10 to the power of 9. Okay, so it will not happen that the k value will exceed the total number of subarrays that you produce from the given array. So having understood all this, let's look at the step-by-step solution, and the step 1 is to calculate the prime score for the given array. Now in this case, the array given is, let's say, 6, 8, 16, 14, 9, and if you calculate the prime score for each of these elements, then you can easily apply the prime factorization method using a simple square root of n approach, you can take the score value to be empty currently, and then you iterate over each of the item. For every element in the array, I will be setting a counter equals to 0, and I will go from 2 to square root of the element, and I will check if I can divide element with the factor I. Then I will increment the unique counter, and I will continuously divide the element as long as it is divisible by the given value I. And after that I will go to the next item. Once this entire process is done, I will be checking if the element left is greater than 1, that means it must be a prime number, and so it will contribute 1 to the count as well. And after counting for the given element, I will be saving the score in the score array. Okay, so score dot push back this count. Now if you are thinking about why did we go till square root of n, I have already explained this in the factors of a number, and that is why I told you that it is the prerequisite for this problem. But just to recap, all the factors occur in pairs except for the square root of n, where you do not find a unique pair, you might find a square root of n if n is a perfect square. In this case, if you consider n to be 36, you will find that 1 has a cofactor of 36. That means if you multiply 1 with 36, you get the n value, which is 36. Similarly, 2 has a cofactor 18, 3 has 12, 4 has 6, and 6 has 6 here. Because 36 is a perfect square, therefore square root of n is also a factor, and its cofactor is the same. So you can imagine that you can actually find all the prime factors from 1 to square root of n, and whatever is left over you can count it here. Okay, so this is the prime factorization square root of n method, using which you can find the score. So for 6, what happens is 6 is having 2 into 3, that means there are 2 prime factors, and that is why there will be 2 score for this 6. For 8, there is only 1 prime factor 2, and that is why the score is 1. So I think you have understood this. It is all about counting the unique prime factors, right? Step 1 is done. Once step 1 is done and you know the score for the array elements, we need to know the score contribution for each of the element, because as you know from the problem statement that if I have to pick k items and my result always starts with 1, then I will always greedily try to pick the largest value and keep on multiplying. Why not? Because that will only maximize my score. But can we actually pick the maximum value multiple times? That is what I have to see, right? So the question here is, which array item is most optimal? The largest item will be most optimal, right? We have to greedily pick the largest item, because whichever item is picked, that will be multiplied. Then how many times can I pick it? Now the number of times that you can pick this 16 will depend on in how many subarrays the score is maximum, right? Now if you consider in how many subarrays it is maximum, there is only one subarray, which is 2, 2, which is only this subarray. Okay, because if you try to extend it on the right side, there is a higher score here, and so this 16 will not be picked up. The score 2 is larger, so 14 will be picked up in that array, right? And if you try to go on the left side like this, then even though the scores are same according to the problem statement, we will be picking the smallest index. Okay, so index 1 will be picked, which is 8, and therefore you will know that for 16 there will be only one contribution, right? So I cannot include it more than one time. Fine. So I hope you have understood. So I will be multiplying this with 16, and then I will be checking what is the next best option. The next best option is 14. Now you have to check in how many subarrays is this 14 contributing. So this value is 2. So to the left side, if you start extending this bracket, you can say the start point you have to take from L to R. If you start extending your L value, you cannot go to 0. You have to stop at this one, and this R cannot go beyond the array size definitely, and you have to stop at 4. So you can take any subarray from 1 to 4, including this index 3, right? And in all those subarrays, this third index item can be picked. But if I ask you about how many such subarrays are present, then you see the calculation here. You have this subarray slice 1, 1, 2, 1, in which 2 is the maximum, right? So since 2 has to be included, I will always include 2, and there are 3 items on the left. And on the right side, if I include 2, there are 2 items on the right. So on the left side you have to have a 2 and on the right side you have to have a 2. I'm just taking the last item of the left side subarray as the same as the first item of the right hand side subarray. In this way you can create all possible cross products. Okay, and if you do that, 2 cross product with 2 and 2 1, you include 2 only one time because this 2 and these 2's are the same. Okay, so you create the cross product 2 with 2, you will get only 2. 2 with 2 comma 1, you will get 2 1. Then you go to the next option, which is including 1 2 on the left side. So if you include 1 2 on the right, if you include 2, then you will have 1 2. 1 2 with 2 1 will get 1 2 1. And similarly you will proceed with 1 1 2 including 2 on the right side, 1 1 2, and 1 1 2 with 2 1 will become 1 1 2 1. Now if you want to understand this in detail how it is done, then I have already given you the prerequisite of Leetcode number 828, which I have already solved in detail. Okay, so I suppose that you now understood how the contribution has been counted. Now if you think about how to check for the boundary L and R, then the boundary L will be defined by the previous greater or equal element, not the previous greater element, previous greater or equal element. Because if on the left side, even if you find an equal element, if you try to include this equal element, then you cannot include index 3 according to the problem statement. We have to always include the smallest index item if the score is same. So I have to find the previous greater or equal element. That you can do with the monotonic stack. If you want to understand that in detail, you have to solve my video on stock span and the online stock span problem. Okay, and on the right hand side you have to find the next greater element, again the same monotonic stack problem. Okay, now if I have determined that for this 2 on the left side, the previous greater element is at index 0 and the next greater element is at, let's say, index 5, then what I can do is I can take the difference between 3 and 0, so 3 minus 0. These many items can be included on the left side, and on the right side I can take 5 minus 3, that means 2 items can be included, and you can just multiply to get the cross product. Okay, so 3 times of 2 will be equals to 6, and these are the number of subarrays that I have formed. 6 subarrays, you count it. Okay, so using the previous greater or equal element and the next greater element, you can exactly count the contribution for each of the element in the subarrays. Now let's say that this 16 was contributing for only one time, and if you happen to include it, your k value will decrease by 2. Now you want to include only 2 times. Then 14 is contributing 6 times, right? And this is the second best option. So out of this 6 and 2, how many times you will be including? Only 2 times, because the requirement is less than the number of contributions, right? So you have to pick the minimum of k comma the subarray's contribution for any particular element. And in this case, since 14 has to be included 2 times, therefore you can multiply 14 2 times, or you can write 14 square. Now in order to optimally calculate this 14 square or any a to the power of b, you will be doing binary exponentiation, right? You will be doing binary exponentiation, and that will take you log of b time, and that is why it is also included in the prerequisite. That means you will be finding a to the power of b using the binary exponentiation. Again, you follow my video on binary exponentiation, right? Now having understood this, let me find out the previous greater element and the next greater element. So in this case, the score is given, and based on the score I have to find out the previous greater or equal element. Fine, so I will be going from left to right simply, and I will be having the previous greater element for the first item as -1. As you know, I will be taking a stack and maintain the stack in non-ascending order. Fine, and as soon as I see an element, I will push it. Now when I saw the 0th element, actually the stack was empty. That means the previous greater element will be -1, and I will push this on top and I will move forward. When I see the top of the stack, I have to always check with the top of the stack. I want to maintain non-decreasing order, the non-ascending order. So you have to check if this element is less or equal. Yes, it is less or equal than the 0th item, which is 2. So it is completely fine. The previous greater element will be index 0, and you have to push the index 1. I am pushing the index and not the value. Okay, Now check it out with the previous greater or equal element. Yes, the first index is greater or equal, it is fine. So I will be saving 1 as the previous greater or equal element, and I will push index 2 and move forward. For this 2, is the second item greater or equal? No, so remove it. Is the first item greater or equal? No, remove it. Is the 0th item greater or equal? Yes, so write 0 here. And can we push a 3 on top of it? Yes, I can push a 3. Okay, and you move forward. Now for this one, what you have to do, find the previous greater or equal element. Yes, the third item is greater or equal. It is greater actually, so you can save the index 3 and you can push 4 and you are done. You are done finding the previous greater or equal element. So for 0 it is -1, for 1 it is 0, for 2 it is 1, 3 it is 0, and for 4 it is 3. Okay, it is fine. So one parse from left to right will help you find the previous greater or equal element. So this will be giving you the L for any subarray start point. Okay, it will be giving you, if you want to include an item, then what will be the start point. Like if I want to include this third item with a score 2, then what will be the start point? It will be after 0, not including 0 but after 0. Okay, that is the meaning of it. Now you also want to calculate the R value for this 2. Like where should I end on the right hand side? So for that you have to find the next greater element. So this is next greater element. Okay, again you will be taking the similar type of stack, and to maintain the next greater element you have to maintain a decreasing type of curve from right to left. Fine. So again I will be giving you the try run, and on the go I will be filling the subarray count as well. So for the first item here, for the first item, do we have anything in the stack? No. That means the next greater item is the n value. N value means it is 5. Okay, so if n value is 5, the next greater element of this last item is 5. Therefore in how many subarrays is this one contributing? I mean this index 4 contributing. Check the L value, check the current index. So 4 minus the left value multiplied by 5 minus the current value, which will be equals to 1 times 1, it will be 1. So only in one subarray it will be contributing. So in the subarray count array, save that this fourth item can be included only one time, not more than that, so that later while doing the greedy pick, if I have to pick the fourth item, then I will be knowing how many maximum times I can pick according to condition, right? And then you push this 4 index into the stack and move forward. Now at this point you check the top of the stack. Is it greater than the current item? No. So you pop it off. Okay, and then the stack is empty. That means on the right hand side the next greater element will be out of bound, which is 5, because I will be assuming it is infinity on the right and minus infinity on the left side. So in how many subarrays this index 3 will contribute? 3 minus what is the previous greater or equal element? 0, and on the right side it will be 5 minus 3, which will come out to be 3 times of 2, it will be 6. So in 6 subarrays this index 3 will contribute, and then you push this index 3 and move forward. Now for this, check the top of the stack. Is this third item score greater than this second item? Yes. So the next greater element of this 2 will be 3. So check out in how many subarrays will it contribute. The previous greater or equal element is at 1, current index is 2. So 2 minus 1 times of, on the right side you have the next greater element at 3, the current index is 2. So 1 into 1 is 1. So only in one subarray it will contribute, and you have to push this index 2 and move forward. Again, is the second index actually larger than the first index? No, so remove it. Now you have to remember that here equal items are not considered, because that rule only applies to the index on the left side, not on the right side. If there are two items 1 and 1 at index 1 and 2, if you are present at 1, then you will always include this one. 2 will not get included, right? Because the smallest index with the same score has to be picked. Okay, now you check with 3. 3 is having score 2, which is actually larger, so you have found the next greater element of this one, which is 3. So the gap between them is 3 minus 1, which is 2. Multiply with the previous greater or equal element, which is 1 minus 0, which is 1. So the total contribution is 2. Save it, and you push this 1 on top of the stack and move forward. Now for this 2, is this 1 actually larger? No, remove it. Is this 3 which is having a score 2, is it larger than this 2? No, so remove it. Now the stack has become empty. That means the next greater element of the 0th item is out of bound, which is 5. What is the previous greater item? It is -1. Okay, so take 0 minus -1, which is 1, multiplied by, on the right side, 5 minus 0, which is 5. So in 5 sub-arrays it will be contributing, right? And then we are done. So this is how using the previous greater or equal element and the next greater element processing, 2 times parsing, you can calculate for each of the items how many times it will contribute if you happen to select the sub-array. This will help us simplifying our greedy pick, so that if we happen to pick an element, how many maximum times I can pick it. Okay. Now step 2 is done. Now we have to do step 3, where we have to do greedy k-picks. Now once we are given the array, you can calculate the score by doing the prime factorization method. Okay. And after doing that, you have to calculate the sub-array count using the next greater element and the previous greater or equal element concept using the monotonic stack. These 2 steps are done, so I have pre-filled all the values. The k value is 3. Now I have to apply greedy pick. You can do greedy pick by using the sorting or the max heap. I will be solving it by max heap. You can always do it by sorting. So out in this entire array, which is the maximum? 16 is the maximum, right? So my resultant score will start with 1, as mentioned in the problem. My k value is 3. Now how many times can I pick this 16, and how will I pick this 16? What I will do is I will be pushing all these items into a max heap based on the element and its index. Okay, so all these elements are pushed into a max heap. Once you are done with that, then you have to take the top of the heap, which is 16, 2. So 16 will be picked, yes, and it is from index 2. So go to this index 2 and look at the sub-array contribution. That means how many times, in how many sub-arrays this 16 can be included, because its score is 1. So in how many sub-arrays is this score maximum, you can say, right? Only in one sub-array. So how many times you can include 16? Only one time. So multiply by 16 to the power of 1. When you want to calculate a to the power of b, remember that you always apply binary exponentiation to solve the problem in log b. In binary exponentiation, you always square the base and half the exponent, right? Now you decrease the k value by that margin, and the k value will be decreased to 2. After that, from the max heap, pick the next best option, which is 14, 3. So 14 will be picked out from index 3. Now check out in how many sub-arrays is it contributing. It is contributing in 6 sub-arrays, right? How many do I need? Only 2. So I will be including it minimum of sub-array count, comma, the k value. So it is 2. So multiplied by 14 to 2 to the power of 2. And this will be our final result. If you just multiply it, you will get it as 3136. Okay, you can just check it out. It will be 3136. So this is the entire process. It involves 3 steps. The prime factorization to calculate score. The second step is the NGE and the PGE using the monotonic stack to calculate the sub-array count. And the third step is the greedy pick using the sorting or the max heap. Okay. And in the last step, it also involves binary exponentiation to calculate a to the power of b optimally. Now, if you calculate the time complexity in the prime factorization method, it will be n square root of the maximum element. Now, the n max is 10 to the power of 5 and ai max, that means any element will be 10 to the power 5. The array size can be 10 to the power of 5. Even though they are not related, but still the maximum value being similar, you can also write it as n root n. But let's write it separately since they are not related. N square root of maximum element. Order of n for the next greater element, order of n for the previous greater or equal element, and also creating the sub-array count. Then n log n for the k greedy picks using the heap or sorting, right? So in this case, these two may be larger. Therefore, we can write it as n square root of max plus n log n, right? And always remember that the k value is less than equals to n times n plus 1 by 2, comma 10 to the power of 9. So this means that you will always get the answer. Fine. The space complexity is order of n for score, order of n for sub-array count, and n for the heap. So all in all, it will be order of n. I hope this all points are clear. Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this code, if you check out, then the first step that we will be doing is to calculate the score. So I will be sending the nums array and the score. Now let me just show you how to calculate it. So this piece of code is something which I have already shown you. It is the prime factorization method. So again, I will not be showing you the same, right? I have already shown you. Then after that, we will be doing the sub-array count. So I will be calculating the sub-array count per score, where I will be sending the empty sub-array count and our previously calculated score. So you check it out how to do that. So this is the implementation of your previous greater or equal element, and then after finding that, we will be implementing the next greater element. And while calculating the next greater element from right to left, we have to continuously update the counter by multiplying the number of contributions, right? So I think you can go through it since you already know the monotonic stack, as I have requested you to watch the videos. Then there is another thing that once you are done with the score calculation and counting the sub-arrays, you will be pushing all the pairs, that means the elements and its index, into a max heap. And once the push is done, we will be taking a long result, and I will be processing until I have assigned all the sub-arrays. So I will be taking the top of the heap, and after that I will be doing binary exponentiation, where if I have to include an element A, then I can include it minimum of the sub-array count, which is B comma K, right? So you will see that it is saying the current dot first, which is A, which is nums I, right? And the minimum of K comma the sub-array count of that given item. So that is what we will be calculating, and always take mod of 10 to the power 9 plus 7. Once you have multiplied it with the result, then the result will get updated, and the number of times you have included, you will be decreasing the value. Now I am not subtracting it by minimum of K comma sub-array count, right? Because even if it becomes negative, the while loop will stop. So I will not care about it. If you look at the binary exponentiation code, it is simple. It is all about taking the result equals to 1, saving all the residual values of power of 1. That means whenever the odd power comes, you have to save 1 power value, and always square the base and half the exponent. That is what we have learned in binary exponentiation. So I think this code is clear. If you still have any doubt, then feel free to comment below, and I'll try to help you as soon as possible. Like and share our video and subscribe to our channel in order to watch more of this programming videos. See you guys in the next video. Thank you.